All right. So we began our discussion of entropy last class in the context of engines, and these are heat engines. And this is the historical approach for considering entropy, because we know that engines allow us to extract work from things. And in fact, if you run a engine in reverse, you can actually do things like cooling. So the engine we've been looking at so far is in the context of getting work out. So like in a car, for instance, you want to be able to extract work for some price, and that price is the energy you put in as Q hot. Okay, and you know that you can just relate this to your everyday experience in a car. You go to the gas station and you pump in, uh, you know, two and some change dollars per gallon. So that's the energy Q hot that you're paying to get work out of that car. So it's not free, and it's even more insidious because all of the heat that you pump in, those dollars that you pump in as gasoline, actually some of that is coming out as Q cold. It's wasted heat. It's wasted Q. Okay. Um, Now you can run this in reverse, and you can run engines that will do things like cool. And so in the summer, like the past summer when we had amazingly hot weather, you were hope maybe you were running AC. That is a engine in reverse. So you do work, and the flow of heat is actually reversed, where now you have Q cold and Q hot reversed. So let's say you're in a very, very cool room in a cool building, right? What you're doing is pumping heat from that cool environment out into the external environment, which is the hot weather outside. So it's the reverse of that. So AC, air conditioning, your refrigerator is also the same thing. That's how you keep things cool. And that heat that you extract from inside that box, which is your refrigerator, has to go somewhere, and that goes out to the environment as Q hot. Okay, so Q hot is not like uh, Q hot and Q cold refer to the reservoirs that accept this heat, and uh, and I'll make that a little bit clearer. Okay, so again, I want everyone to just chime in, unmute yourself, and chime in if anything is unclear as I discuss. Okay, so here's the Carnot cycle in the context of extracting work that we saw. It's an idealized process. Everything is reversible, and it uses an ideal gas as the fluid. Okay. So it's certainly the most ideal uh, cycle that we can envision to consider as a baseline what we can have as efficiencies in systems. Okay. And through this analysis, I won't go through the whole Carnot cycle. It's in your text. I'm sure a lot of you may have read it already, and the lecture will be posted. So these are the four steps. You have two compression and two expansion steps, and symmetrically, you have two isothermal steps and two adiabatic steps. Okay, the isothermal steps occur at T1 as the system goes from equilibrium state 1 to equilibrium state 2, and that T1 is going to be the same for state T2 because this is isothermal. Okay, and it's reversible. And that's where you have influx of hot, Q hot, and you need Q hot for expansion of the gas. And then you have this adiabatic step where you have further expansion from state 2 to state 3. And here now you have change in temperature from T2 to T3. And that's okay. We don't worry about it because we know temperature can change in an adiabatic process. And that T3 we call is lower than T1. Okay, just because it's at a lower pressure, that whole process, then that reverse step, the isothermal step back to state 4 from state 3 occurs at T3 because it's isothermal. Okay, and so the temperature here at state 4 is T3, and then you go back to 1 to complete the cycle to an adiabatic compression. Okay, and we allowed our T hot to be T1 and our T cold to be T3. And we know that this is also equal to T2, and we're going to make use of this equality. So let's just keep this in mind. Okay, this is pretty obvious from the graph. and the nature of the processes involved. Right, so T hot is really just this temperature that the upper isothermal process, and T cold is the temperature of the bottom, the lower isothermal process, which is a compression. Now, we know that the volume represented in this curve is the area, is the work, the area is the work. So we can try to say, all right, well, the question we can ask is, well, we know we have to put in heat and we get work out. And so what's the efficiency of this engine? Okay, we might be interested in the efficiency. And for that, we can look at the first law, which we did. And we looked at the integrated first law because we start with the differential form, which is this. Okay, and then we integrate it over the cycle because we know that since U is a state function, integrating that state function over a cycle is going to lead to zero for that integral. So that's a useful piece of information that we can we can exploit in our analysis. So if we do this integral over the cycle for du, we know that we get delta u, and that's going to be zero because u is a state function. And so that allows us to then get a relationship for Q and W. And we have two sources of Q in this case. Okay, the two sources of Q are the Q hot and the Q cold. Okay, so that Q then just becomes decomposed into a Q hot and the Q cold in our analysis, first law analysis. And then we only have one work, which is the area under the curve. So there's just one W. And we can use simple algebra to isolate W on one side, and we see that's just equal to the negative of the sum of all the heat interactions. W is just minus Q, and Q is the sum of Q hot and Q cold. So we have W is just equal to the negative of the sum of all the Q interactions between the system and the surroundings. And then we can define the efficiency for this engine. We call that the Carnot efficiency. It's an ideal efficiency, epsilon, and that's defined as minus what you get out, which is work, divided by what you put in, which is that hot, Q hot, right? Just as in your car, Q hot would be the gasoline, the heat that you would get from the gasoline sparking, okay? And so when we put in our expressions for W into this expression for epsilon, we see that this is equal to the negative. Now we're looking at this expression here. We get the negative of W, which is minus Q hot plus Q cold divided by Q hot. And the negatives cancel. So on the top, we just have Q hot plus Q cold here divided by Q hot. And now we can just divide the Q hot plus Q cold in the numerator individually by Q hot. We'll get two terms. So the Q hot divided by Q hot is equal to 1 plus Q cold over Q hot. And that's how we get this expression for our ideal Carnot efficiency. Okay, so it's very simple. It's just 1 plus Q cold over Q hot, this ratio, Q cold over Q hot. That's the ideal efficiency ever. Okay, that's what you have to compare to if you ever want to develop something that, you know, in this modern world, everyone is after energy and batteries and whatever source of power and energy you're looking for in work. You have to compare your efficiency to the Carnot efficiency, which is the highest. And the depressing thing about the Carnot efficiency, if you recall our sign conventions, SIGN for Q, we know that Q cold, since it's leaving the system, Q cold exits the system and Q hot enters the system. Again, you can always refer back to that car engine analogy. The Q cold would be what goes in the radiator. That's why you need a radiator and the cooling fluid. So that's leaving the engine, okay? So Q cold is going to be negative, Q sub C is negative, and Q sub H, Q hot is positive. So the term that is being added to 1 is negative. which means that epsilon Carnot is going to be less than 1. Okay, and it won't be equal to 1, it will be less than 1, because in reality, we know that we have to have this Q cold. Okay. Now, there are arguments to prove why that Q cold must be there. I'm not going to spend time on that. I might put this as a separate proof for you, but if we didn't have that Q cold, we could devise process. So let me just, you might be asking, okay. So let me just finish this point. So epsilon Carnot is less than 1. Okay, and that is really another one of these things for wonderment. Okay, for me, you know, when I always do thermodynamics and I see this very simple equation, but yet it's very profound, because even in the most ideal case, your efficiency is less than 1. You're never going to get 100% efficiency. Okay, it just boggles the mind when you think about it. And in fact, the math actually just works out this way. So, you know, anyway, I can go on and on. This kind of stuff makes me go like cool stuff, you know. All right. Anyway, so I haven't proven to you that Q sub C has to exist. Okay, and you might be asking, well, you could just say, well, why not? You know, first law doesn't forbid QC not existing. You know, the first law says, well, if I put in Q hot, it can all come out as W, right? So if we go back to our first law analysis, right here, right? If there was no QC, there would be no problem from the point of view of the first law, okay? Because the first law is still satisfied. W equals minus Q, and in this case, it would be minus Q hot, okay? And in theory, you would have 100% efficiency. There are some arguments, and I'll post these independently, but there are arguments. One can argue one can argue and prove that QC must be present. Okay, and I won't take time. I'll just tell you that. Okay, and so for those of you who might be thinking, well, you know, why is that? I'll put this independently, but I'll just tell you right now that QC must exist. And in fact, the take-home message of that argument or that proof is that if you didn't have QC, you could devise machines that would effectively take heat from a cold source, like let's say, you know, the inside of a refrigerator, if it were cold already, and pump that heat out to the outside, which could be your, you know, outside of the refrigerator in your home, or outside into the atmosphere, the you know, outside of your home, without any work being done, without any net work being done. And that would violate a lot of principles, namely that what would happen is that without net work being done, right, what you would have is you would have a cold environment. And here's your hot environment. Let's say this is the outside and this is the refrigerator. What you would have is Q flowing this way without any net work. Okay, and you know that that's essentially spontaneous flow of heat from a cold system to a hot system. Okay, yikes, that doesn't happen in reality. Okay, so that's the whole point. That's why you have to have QC. All right, enough said with that. Any questions so far? Okay, so we have our epsilon Carnot, and so we can write then that epsilon Carnot, which is equal to minus W over Q hot, right? We can actually now play games with this. So we can actually say, well, if you're given an efficiency, so given efficiency, what is work? You could actually get what is work for a given QH. So that's just equal to W is equal to minus epsilon Carnot times Q sub H. And so this would be the output work, or work done by the system. Okay, and that's why we have a negative sign, because we know epsilon is always going to be greater than 0, and Q hot is going to be greater than 0. But from the point of view in our sign convention for work, work becomes negative, and that's okay because the system does work. And this is exactly what we defined. Okay, and so this is a way to get work out of a problem where you're given a Carnot efficiency and some way to get Q hot. Okay, so if in a problem, you might do first law analysis or some other analysis, or you might be given Q hot and the efficiency, and you might be asked to compute how much work would you get out of a machine with this kind of a setup. Okay, so that's one application of that. Okay. So, and the other thing now, we can say that this is equal to 1 plus Q cold over Q hot. Okay, so we have here a very important relationship. Okay. Now, it's okay if you go back to our analysis here of the Carnot cycle, or this picture of the Carnot cycle. We have our efficiency in terms of Q hot and Q cold. Okay. It's actually a little bit more satisfying if there was some way we could formulate this efficiency in terms of temperature, because that actually would make our lives a lot easier. Why? Because you can compute the efficiency because temperature is something measurable. Okay, Q hot is a little bit more difficult, even practically, to access as opposed to temperature. You can stick a thermocouple, you can stick a thermal sensor into a machine, and you can read out a temperature, right? But to get Q hot and Q cold, you have to do some calculations. There's no meter that you can stick into something and say, oh, well, this is the heat interaction that we're seeing. It's all through temperature. And remember, our sense of heat is really based on temperature. The hotness or the change in hotness of something really is correlated with temperature, right? dQ is Cp dt. So if we can get a way to connect temperature to efficiency, that would be really useful. And in fact, just as insightful as our discussion about or using Q. So that's where I want to head next, is to see if we can transform our expression for epsilon, the efficiency of this ideal system, the Carnot system, which already has given us some insight using Qs. Can we relate this in terms of Ts, which are the temperatures, T cold and T hot? Okay, so that's what I want to consider now. Okay. So before I do that, I just want to show that another representation of Carnot engine. And this is something, again, those of you who have done the reading or maybe just Googling it on the web, you might have seen it, is this. It's just a representation, but it sort of is a synopsis of everything. So let's say you have a heat reservoir, and we call that the hot reservoir. And I'll tell you what a reservoir is in a moment. And this hot reservoir is maintained at pH, T hot. And that was our T1 and T2 in that Carnot cycle graph. And then you have another reservoir, which is the cold reservoir. And I'll put hot and cold here in quotes because these are just relative words. They're relative to one another. So the cold reservoir is colder than the hot reservoir, but in terms of absolute temperatures, it may mean nothing. So this is the cold reservoir. Okay, and this is maintained at T cold, which was T3 and T4 in our thing. And so these are called hot and cold just relative to one another. Okay, and again, in that Carnot cycle in the PV diagram, you saw that you needed to have some isothermal process. So you needed somehow something that would keep your system at a particular temperature. And you can think of it this way, right? If you wanted to keep your system at a particular temperature, you would need something that would take up the heat. So as this gas is expanding, right, in the first stage of our Carnot cycle, when you have that expansion isothermally, we know that when things expand, a gas expands, its volume increases, right? So heat is being added into the system, okay? But that heat has to come from somewhere. And in this case, it would have to come from this hot reservoir uh, that the system is associated with, such that the gas expands, okay, as you add heat into the system. Okay, so that's what this hot reservoir is. And the important thing about any reservoir is that its temperature doesn't change. Okay, so again, a heat reservoir, some examples in real life of hot and cold reservoirs, really just reservoirs. And these reservoirs are just things that whose temperatures don't change. They're always at equilibrium. They're always at equilibrium. Okay, so the reservoir is always at equilibrium. Is always at equilibrium. So if it has any exchange of heat with any system, okay, the heat interaction of the reservoir with the system is always reversible because the system, the reservoir is always at equilibrium. Okay. Does that make sense? So examples of reservoir: oceans, large bodies of water, right? For all intents and purposes, the ocean, you know, if you're like, let's say a chemical plant or a chemical producer, and you have a plant next to an ocean, for many years before environmental laws were passed, these types of facilities would dump hot water or excess heat into the local bodies of water, and I just use the ocean as an example because in the grand scheme of things, the ocean temperature, though it may have a small fluctuation in time, it's so large that it's not perturbed in the grand scheme of things. Okay, so another example is the atmosphere. Okay, of course there are daily changes in temperature due to weather and stuff, but it's such a big reservoir that you can just dump stuff in, and you can assume that it's always going to be at a particular temperature. Okay, so abstractly, that's what we mean by a reservoir. Its temperatures don't change, and the reservoir always stays at equilibrium. It's so big compared to your system that any interaction between the system and the reservoir doesn't perturb the equilibrium nature of the reservoir. So the reservoir may accept heat or deliver heat to the system, but the reservoir is always at equilibrium. So that's what these hot and cold reservoirs mean. So for the Carnot cycle, then you have a hot reservoir that's going to deliver Q hot. Okay, so we have Q hot. And then this circle is going to represent our engine, E. Okay, so we have Q hot. The engine operates reversibly in a cycle. Okay, and then out of that, we get work. Okay, and then I haven't proven to you this, but there is Q cold that is dumped to the cold reservoir. Okay. So in the case of a car engine, the Q hot comes from the gasoline, the spark that heats up your system, okay, which is usually some sort of gas in the cylinder. Okay, so that the engine runs hot, you spark that fuel. The engine cranks out, you get work, but there's some waste heat, which is Q cold, and that Q cold goes to the cold reservoir. And what is the cold reservoir in a car, perhaps? Can anyone sort of now get the analogy? What would the cold reservoir be in the car engine setup?
Maybe be the coolant tank.
Yep, exactly. It's whatever you have as your system to cool the engine, the radiator, the coolant tank, everything like that. That's exactly right. Okay. And we assume that that coolant, and you see here that you really have to assume that that coolant tank or that coolant system is pretty much at equilibrium or is not going to be perturbed too much, even though it accepts heat, right? Because if that system were to actually heat up as it was getting heat from the engine, it would no longer be this reservoir to accept that heat that's being expelled from that engine. You'd have trouble. You'd overheat on the highway. Okay, and so again, another very palpable example of what these reservoirs are. So in your system, that's exactly right. The cooling system is your cold reservoir. And of course, that cooling system is not cold. If you ever have touched a radiator after you've driven a long time, that radiator is not cold. It's quite hot. Okay, and that's why it says on the radiator, do not open after, or be careful when you open that radiator. Okay, so I hope this car analogy is useful to you when you look at these things in an abstract sense. So this is the representation of the Carnot engine in a different way. It's the same thing, but it allows you to understand the concept of a reservoir and this engine that operates cyclically and reversibly. Okay. All right, so let's move forward. Any comments or questions? Okay. I'm gonna move on to do a first law analysis now. So the question is, okay, so back to our question. How to connect epsilon Carnot, the Carnot efficiency, with temperature. So T hot and T cold. Okay, so that's the question that we want to address right now. So we know that epsilon Carnot is equal to 1 plus Q cold over Q hot. And what is this equal to as some function of T hot and T cold? That's what we want to know. What does that function look like? All right, so we're going to do first law analysis because that's the only law we have so far. Very soon we'll have another law now. Or we have the zeroth law. So the first law analysis of the stages of the Carnot cycle. Okay, that's what we're going to do now. Okay, so let's start with 1 to 2. So this was isothermal, right, and reversible. And it's an ideal gas. That is our system. Okay. So we know that for an ideal gas, U is only a function of temperature. But in this case, temperature doesn't change. So delta U, 1 to 2, is equal to 0. Okay. So 3 pieces of information here, and we've used all of them to get delta U very easily to be 0. What that means then is that Q hot, right, because we're going from 1 to 2, that's Q hot, is going to equal minus W to go from 1 to 2. Okay. And what would that be? So Q hot is going to equal minus the work to go from 1 to 2, and that's reversible. So that's going to equal minus P dV. And that we have to do an integral, right, from V1 to V2. So what that means is, in our Carnot process, we're looking at the process where we go from equilibrium state 1 to equilibrium state 2. This is an isothermal process. In that process, temperature doesn't change. Delta U is 0 for an ideal gas because U is only a function of T. And the only thing that we have coming in is Q hot. Okay, so that Q hot must be equal to then the minus W for this process. Okay. So that's what we're after here. And we're going from V1 to V2. Okay, so on the volume diagram here would be V2. And we start at V1. Okay, and so those are the limits of our integration here that I've shown. So Q hot is equal to the integral from V1 to V2 of the negative of minus PdV, where P is your pressure from your equation of state. So we can say that this is just the integral from V1 to V2 of PdV. But we know that this is an ideal gas, so P is equal to nRT over V. And since this occurs isothermally at T hot, which is just T1 or T2, right? So we can let this be T hot for the moment, because this is going to be a constant temperature, which is T1 or T2. Okay, so Q hot is equal to the integral from V1 to V2 of pressure, which is just nRT hot dV over V. And we'll let n be constant for the time being. We're not gonna, we can take 1 mole. We'll add the ones in later. So this is just going to equal nRT hot natural log V2 over V1. Okay, so that's Q hot from that first process 1 to 2. So let me just write that. Q is equal to nRT hot natural log V2 over V1. Okay. Any questions on that? Okay, let's go to process 2 to 1. Okay, so I'm going to let this be equation 1 with the capital. Okay, so we'll let that be. So now let's go from 2 to 1. Sorry, 2. What am I saying? 2 to 3. Okay. Now we'll go from state 2 to 3. And this was the adiabatic reversible stage. Again, we have ideal gas. Okay. We know that Q is 0 for this process because it's adiabatic. Okay. And therefore, we can write du is equal to dW. Okay. But we know that for an ideal gas, du is just nCV bar dt. Okay. And so then W, to go from 2 to 3, is equal to the integral of nCV bar dt. And that's going from T2 to T3. Okay. But this is just equal to nCV bar T3 minus T2. But what is T3 minus T2? Let's see here. T3 is T cold and T2 is T hot. So T3 minus T2 is T cold minus T hot. So W2 to 3 is equal to nCV T cold minus T hot. Okay, and then Q2 to 3 is equal to 0 because it's adiabatic. Okay. Now remember from our initial, so when we talked about reversible adiabatic processes, we had another conclusion from earlier. So I'm going to write this down. Earlier analysis of adiabatic reversible process for an ideal gas. We came up with a conclusion. We were able to do this relationship that we would have T2 over T1, okay, is equal to V2 over V3 raised to the gamma minus 1. Okay. So T2 over T1, what's T2 over T1? Let's see. T2 is T hot. Wait a second.
Looks.
Sorry. Yeah. Go ahead.
No, I was just gonna say they're the same.
Yeah. You're right. I'm just checking. So from 2 to 3, we're going from T3 to from T2 to T3, and T3 is T cold. So in that ratio, we would have T cold over T hot. T cold over T hot. So actually this is T cold over T hot. Okay, because T cold is your final state and your initial state is T hot. So this is from our earlier analysis from a couple of lectures ago, where we related temperature to the volumes in an adiabatic reversible process. So this is what we find here. Okay, any questions? So we'll make use of this a little later. I hope I haven't I made a mistake, but you can catch me if I have. It'll come up later. Any questions? So this is a result we've already seen, so I'm not going to rederive it. You can, it's in the previous notes. So now we can go isothermally from 3 to 4. Okay. And I'm not going to rewrite everything because we now should be able to sort of think about this. It's an isothermal process. So delta U is going to be 0 to go from 3 to 4. And Q, and so this Q is going to be Q cold, right? Because this is at that bottom stage. So this is going to be Q cold. And that Q cold is going to be minus W to go from 3 to 4. And again, that's just going to be, let's see, the integral from V3 to V4 of PDV. Okay. But that's just going to equal nRT cold natural log V4 over V3. Okay, so if I have everything right, that's what we have. Right, so Q cold is equal to nRT cold natural log V4 over V3. Okay, so this is equation, I'll call that equation 2. Right, so this for stage 3 to 4 is the same thing as from 1 to 2, which was isothermal, but now we're just using different subscripts and the temperature is at T cold. So now we're at T cold because this process occurs isothermally at that cold temperature because the system is expelling heat to the cold reservoir, and cold being in quotes because cold is cold relative to the hot reservoir. Okay, and then finally, we're going from 4 back to 1, which is the adiabatic and reversible process. So we know that Q 4 to 1 is 0. We don't have to worry about any heat interactions. Okay. And W to go from 4 to 1 is just going to be NCV T1 minus T4, but that's just going to be, that's CV bar and CV bar. T1 is T hot and T4 is T cold. So we have that. Okay, we have that. And again, since it's adiabatic and reversible, we have a relationship between temperature and volumes. Okay, So we have a relationship for a reversible adiabatic process. So in this case, it's going to be T hot over T cold is equal to V4 over V1 raised to the gamma minus 1. Just as we had here for this other adiabatic and reversible process, here we had a relationship between temperature and volume for adiabatic reversible. We have an analogous relationship here for the final adiabatic reversible process. And you'll see here that the T colds and the T hots are just reversed. But we do have this relationship between temperature and volume. Okay, so let's see what we can get at here without any confusion. Everyone follow so far? So this was all first law analysis. There was nothing besides first law in all of this and things we've already seen. Okay. All right, so for our Carnot cycle now, we have all of the Q's and all of the W's. Okay, and so now let's go back. So we were interested in epsilon Carnot as some function of T hot and T cold. And we don't have to worry about T1, 2, 3, 4 because there's really only two temperatures in this engine, the T hot and the T cold. You could use 1, 2, 3, 4, but there's only T hot and T cold. So that's what we're going to worry about. So what is epsilon Carnot as a function of T hot and T cold? So we knew that this was 1 plus Q cold over Q hot, but now we have expressions for Q cold and Q hot based on our analysis, first law analysis of all of the steps. So we can write Q cold and Q hot in this expression. So let's do that. Epsilon Carnot, which is equal to 1 plus QC over Q hot. We just computed QC and Q hot. Here is QC. Okay, and Q hot is here. Okay, so all we have to do is substitute in those expressions in that ratio of QC over Q hot. Okay, so the NR is going to cancel in that ratio, so I'm not going to worry about NR. Okay, so what we have is QC over Q hot. So the first things we'll have are TC over T hot. Okay, so this is going to equal 1 plus TC over T hot, and then we're going to have this log, all this log stuff. Okay, so the QC has this log of V4 over V3. So I'm going to write that on the top here. Log of V4 over V3. And then the T hot, or the Q hot term is going to have a log V2 over V1. That goes on the denominator. Log of V2 over V1. Okay, is that, so far we have this, okay, we're getting there. So now we have something that has T and T cold and T hot introduced for our expression for the efficiency. So that's good, we're making some progress. Okay, so now let's ask, what's this ratio of logs? Okay, so what can we do about this ratio of logs? So let's see here. Let's write this. Let's make use of these expressions that we had earlier on. Okay. So let's make use of this expression. Okay. So what if I wrote this? So we have T hot over T cold is equal to V4 over V1 raised to the gamma minus 1. Okay, and that's coming from this expression again, right here. Okay, I just rewrote it. Now, what I can do is if I raise both sides to the -1, okay, if I raise both sides to the -1, I can rewrite this in this manner. T cold over T hot is equal to V1 over V4 raised to the gamma -1. Okay, so what I've done here is raise both sides to the -1. Okay, so on the left, I flipped T hot over T cold, so that became T cold over T hot. Yeah. And on the right, what I did was I raised that ratio V4 over V1 to the -1. So I flipped that, so I get V1 over V4, and the gamma to the raised to the gamma -1. That doesn't change. Okay, so that's equal to T cold and T hot. Any questions? Any questions on what I did there? Okay. So now let's see. Now what do we want to do? We have to be very careful here. So we made use of this expression. Now let's see, we have one more expression here. We have another expression here. Okay. So we're going to make use of that expression too. That's T cold over T hot. That's T cold over T hot, right? We have T cold over T hot here. So T cold over T hot, according to this expression, is V2 over V3 raised to the gamma -1. So T cold over T hot is V2 over V3 raised to the gamma -1. Right? So what this is saying is that these two guys must be equal. Okay, so it must be saying that V1 over V4 is equal to V2 over V3. Okay, everyone see what I just did there? And so now we can rearrange this guy to say that, okay, V4 over V3 is equal to V1 over V2. And that's just a simple algebraic manipulation. Okay, bear with me, we're almost done. We're almost done. Okay. So V4 over V3 is equal to V1 over V2. Everyone okay with that? Any objections? No, there will be no change to 1 minus gamma, Nate. No, I just saw the chat. Nope, everything is fine. Go back and check it, everything is fine. So we can now use this expression, okay, here. Okay, we have V4. So I'm just going to write this down. I don't want people to get confused. So I'm just going to write it down and we'll continue on Monday. I see it's 11, but just bear with me for a few more seconds. So epsilon Carnot is equal to, we'll use this part, 1 plus T cold over T hot, natural log on the numerator, we have natural log V4 over V3, and on the denominator, we have natural log V2 over V1. But we have this relationship right here now between V4 over V3 and V2 over V1, okay, which is equal to 1 plus T cold over T hot, natural log V4 over V3 is equal to V1 over V2. So what I'm going to do is put V1 over V2 here, and then on the denominator, I have natural log V2 over V1. And I'm going to stop here because I'm running out of time, but I want you all to go over this at your leisure Everything is right. All the exponents are taken care of properly. There was a question from a student, because this is the final result that we want. And so I will stop here. We'll finish this because those log terms are going to disappear. I think some of you will already have jumped the gun and see that that happens. But we will continue this on Monday, since I've run out of time. So thanks for your attention and sticking around. Any questions? I'm still going to entertain questions. Okay.
Thank you.
Oh, sorry, go ahead.
Thank you. Have a good weekend.
Okay, thanks. You all have a good weekend too. Be safe. Enjoy.